Okay, so this is what we are doing. Then the advantage for the numerical, you can solve the real life complicated problems. Then you can results can be achieved very faster, and the result can be achieved on entire geometry. So that is what you can see. You have the entire geometry. On the entire geometry you can achieve the results. I have to come back and I have to add and then this is one of the advantages, and applicable even if physical prototype is not available. So what does it really mean? That if you don't have the small prototypes of it, you don't have the experimental parts, you can still do the analysis. Of course you don't need the experimental one. Of course experimental one is needed to validate, but apart from that you don't need the experimental one. And in the experimental part you can see these are the advantages. So we are generally more focused on the numerical part. That is what the finite element simulation is. So now coming back to the finite element process in the user perspective, you have to know, you have to define the problem. First of all, want to know what you have to do. So any problem you have to define that first. And then you have to create a clean model. So the problem is defined and this is the model which has been created. Okay, then you'll have to apply the boundary conditions. So this is the constant here, the load is applied from here. So these are the steps which you have to follow in a finite element software. Then you'll have to break up the model. So you'll break up the model into small parts, small finite parts. You can see here the model has been break up in small parts. You can see here the line has been able to successfully break up the model. Then you'll have to define the analysis methods, and finally you'll have to submit the job, and then your post processing will start. So this is the post processing, means the result, the working is start. There's a pre-processing where you'll make the model, CAD model, geometry, and then give the boundary condition, define the mesh and everything, and the post process is this. So now come back to this slide. So this is the process of FEM, the same thing in a more interesting way. So this is your simple geometry, a rectangle, suppose a rectangular plate on which you are going to do an analysis, any analysis. Suppose a rectangular plate you are going to heat up. Then what you'll do is that you'll divide the rectangular plate into multiple finite elements. So that is why the whole thing is called finite element. So you'll have this, you can see you have divided it into multiple elements. One square here is one element. So this is simple, and the intersection point is called node. Then after that what we have done is that the each element is uniquely identified, and the problem for the each element is solved uniquely. So this is all the mathematics part of it. We cannot see that in the software, but this is important to understand. Okay, so we cannot see this part in the software. Then you'll have, once the problem of each part is solved, so that is then assembled to obtain the nodes for the entire domain. So you'll assemble that, the problem, the whole problem, mathematical problem for the individual parts are assembled together in one big complex. Again, that is a part of the software, which software does in the internal calculation, something we cannot see. So what we can see is, we can see this CAD model, we can see how we are meshing it, and then engineers will do their own mathematical modeling inside, which is already built in the software. You will model it, and then we'll finally see this kind of result. So this is what it involves. This is what the process is. So in short, we can see that from CAD model to a final, full and final application. So you'll have this CAD model. Now you can see this is a CAD model over here, right? So this is a bridge. So now an engineer is analyzing the bridge, that how much the bridge is acting. So this is where the load is going to be This is where the people are going to walk, the bus and different vehicles are going to move. So this is the part, this is the base part where the load is going to get applied. Okay, so suppose we have to monitor this part. So you will make a basic finite element CAD, basic CAD model of it. Then you will import that CAD model into your software. So once you import the CAD model into your software, now you have to uh, divide this into finite number of elements. So that is what is called meshing. So we'll come to see the what is meshing in more detail. So you'll divide it into finite number of elements. After that, you'll apply the loading condition. So you'll have to see what does the loading condition means. The loading condition here means sorry, uh, what does the loading condition means? Hmm, let me just go back and ask again somebody that anybody is aware of loading condition. What does loading condition means in finite element? Please record the meeting. Okay, I have started recording. Anybody? Yes, anybody has any idea what is loading condition? Yeah, we apply the load. Uh, Somewhat similar. Yes, we apply the load, but we don't apply the load in this way. But okay, fine. Anybody else who can say something about it?
So load the bridge and
Load the
other
base. So,
vehicles.
yeah, so basically the loading condition is that whatever the applications you are whatever it is, the loads are applied, whatever the things which are moving there, or whatever application it is used for, so that application will stress those parts. So therefore we apply the loading condition here. We apply those forces or those temperatures over there which the part is subjected to. So for example, a part which is subjected to high temperature, so the loading condition there will be the high temperatures will apply. The part which is subjected to high force, so the loading condition will be applied is forces over there. So this particular part here, because the people are moving, the transport vehicles are moving, so the loading condition in this case will be the force which we are going to apply over there. And of course, before that, one thing is missing over there in the model is that we have to give the exact material. So that becomes very important. Okay, so you have to give the exact material on which you are going working. And then finally, after that, the softwares will give that how the loads are distributed, how the stresses are applied, and which area are the most critical area. So again, you can see in this that this is the start of the bridge. The start of the bridge, you largely have blue areas. That means the stresses which are acting. This is a blue area. The contour is showing stress. So yeah, equivalent stress, the contour is showing equivalent stress. So equivalent stresses which are acting here are very small. However, as you move forward and you come at the middle of the session, the equivalent stress becomes large. So now then this part becomes a very high subjected to a high equivalent stresses. So it will give an indication to the engineer that this particular region is a critical region, and this particular region we are going to monitor for the failure. Maybe you can plan the maintenance, maybe you can strengthen that particular region more, maybe you can use the material, you can have a composite base structure where the this material can be of higher strength and all. So all these application you can plan. So this is all before the bridge building. Okay, bridge is not built. This is the whole thing, whole analysis is before the bridge building has even started. So similarly, you can see that finite element modeling defines the effect of different parameters. So you can see effect of vibration. So we all know that how the vibration will happen. Vibration will happen when the things will move. So how the effect of vibration is, how much it is vibrating. So again, you can see this particular part in the center is vibrating maximum. So that means this could be subjected to more failure. Then the stresses which are acting due to the dynamic load is very much similar here. So these are this all gives you basically this all these things, all these pictures, and then there are many more. This all gives you an outcome of what we are going to actually do with the sort of how we are going to analyze this one. Fine, you can see the fatigue life. So here the figure is little bit small, so the monitor, you can see here this particular structure is minimum and this particular structure is maximum. So therefore the engineer will get to know that this particular structure, due to the vibration and due to the various load cycle which are happening, this particular structure can fail earlier. So therefore the engineer, what engineer will do is that either they will perform the maintenance for it, or they can replace the material from the existing material to those material which have the higher fatigue life. So all these things can be done. Now imagine, before this analysis, if we are going to just make a bridge and we don't know where it's going to fail, where the susceptible area and all of a sudden the bridge fails, then we'll be having a big problem. So these are some of the effects. So coming back to, so now again, let us understand that what is So again, let us understand that what are the different steps in the finite element analysis. So this slide is very important and very critical. We need to understand that what is the task of an engineer. So you as an engineer, what is your task and what is the task of the software? And the third thing is that what the engineers who are developing the softwares are basically doing. So the engineer task is that we'll define the problem and we will discretize the problem. Okay, and that is what we are going to see today in the session and tomorrow in the session. The definition of the problem will be defined, the CAD model will be drawn, the boundary conditions will be given. All these things we will see today. Okay, and tomorrow, sorry, all these things we'll see in the today's and tomorrow's session. And finally, this part, validation and post processing. This whole part is what the software will be doing, something you cannot see. Once you'll start, you'll discretize the model. Discretize means you'll divide the model into different elements, as we can see over there. Once you'll divide the model into different elements, the whole thing, the software will calculate internally your results, and on the basis of that, the software will define that what you have to basically do. The calculation will be defined by the softwares. So now this particular part, you can see this define the problem, discretization, post processing, and validation and post processing. This is the task of an engineer, the finite element engineer, and these are the software tasks which the software is performing the internal calculation. But again, for these three things, somebody has to develop all these things, somebody have to develop the mathematical part of it. So again, that is something which the engineer does. So now here you see what is the mathematical discretization, the second part. So you'll have, suppose, a bar, a cantilever bar or a fixed bar, not the cantilever one, a fixed bar which is fixed. Okay, and this is subjected to the load over here at this particular part. You can see this load, and this is having a torsion. So the loading condition which you have to give in while modeling the software is that you have to apply the load. Here there are two loading conditions. So in the user interface, we'll see you'll have to define load 1 and load 2. So there are two loading condition basically. This is load 1 and this is load 2. So load 1, you will give a downward force, downward force in this direction. Load 1 you'll do a downward force in this direction. Load 2 you will apply the torque moment in this direction, in the anti-clockwise direction. And then you'll first define the problem and your discretization is complete. Then you run the problem, and this whole calculation the software will do themselves. So again, these are the steps. Create the finite element, that is discretization, approximate the solution. So we have already seen the steps. So we can see that step 1 to 6 are the part of the method. So when somebody study finite element as a subject, finite element analysis as a subject, so the person calculate do from 1 to 6. This is the mathematics which we study. Those people who have already studied this as a subject uh, will be interested, will understand that, and those who are not, I hope that I can generate enough interest with today's presentation that they will study this as a complete subject. So the first to six, step 1 to step 6 is what you are basically being taught in the subject. Again, we have seen the mathematical concept of discretization. So just go again here. So this is element L1. Element 1 has a certain mathematical analysis matrix. Then element 2, element 3. So suppose this is a simple truss. Okay, you are applying, this is node 1, node 2, node 3, and these are the three elements of the truss. So the whole element you will assemble into the form of matrix. So don't worry about these complicated mathematical equations. Of course, this is not the part of it. So this K is a one big equation of the which defines the whole this. So it's called global stiffness matrix. So here you can see the global stiffness matrix, and in terms of phi 1, phi 2, and phi 3, these are the directions at which this happening. So you'll have this particular part, this particular part, and this particular part in one matrix of whatever this 3. So you'll have 3 by 3 dimension matrix. So you'll have this, then you'll assemble it. So how many nodes are there? 1, 2, 3, and 4 nodes, and one each element has two nodes. So for each element you will get 2 by 2 matrix, which is something like this. You can see a spring element as 2 by 2 matrix, and then you will combine it, and depending on your number of nodes, there are 4 nodes. So in this case you will get a 4 by 4 matrix. Okay, 4 by 4 matrix. So now imagine if we'll have to have this much big element, this much big bar, and we'll have to discretize it like this, and we want, instead of 3 element, we want 150 elements. Suppose this bar is of 150 length, and we want to see the analysis at every 1 length. So you'll have, in all you'll have 151 nodes. So 151 nodes means your matrix will be 151 by 151. So can you, a human being, solve the equation of 151 by 151 matrix? So अगर हम इसको ऐड ही करेंगे तो आपको एक मैट्रिक्स में फिलअप करने के लिए ही you will need all these elements. So how many elements will basically have 151 by 151? So if we are going to go there,
Hello. Sorry, guys. We Doctor Ahmad Umar has lost the connection and he's trying to resolve it. Meanwhile, please have patience and wait. He will be joining us soon.
Okay, so I'm back. We have lost the connection. So where? Just let me reshare the screen first. So this is what we are seeing. So I was saying that if we'll have such a big set of elements, am I audible to everyone?
Yes, sir.
Yeah, somebody raise hand. What is your doubt? Irfan Mumtaz. Okay, okay. So let us
Yes,
just
sir. Your voice is audible. Yes.
okay. Just continue with it. Okay. So I was saying that if there's a large chunk of elements, suppose there are 3-4 nodes only, we divide and we want at 1 mm each the solution. We want to see that what is happening at the interval of 1 mm, and if the whole thing is just 150 mm long, so we'll have 151 nodes. So 151 multiplied by 151 will be how many elements in a matrix? So let me just 22,800 elements. So that is something which is not possible for us to solve manually. 22,800 element matrix to solve manually is not possible to us. So that is why what we do is that computer made it, make it very easy and very efficient. So this is what I was saying. Now coming back again to the advantages. So some of the advantages which it does is that it displays the results in graphical form, to which make it easy to analyze. It allows the engineer to make decisions, design decision and recommendation modification. So that is what uh, we have done last time around. That is what I have told in this picture, that it allows the engineer to make modification, the design modification, a structural modification by just looking at material modification and different kind of modifications. Then it provides the greater flexibility in the design and analysis and the easy to use interface. So it displays all. You can see this whole image here. You can see that this particular image, this is your turbine blade, and here more stresses are generated. So one of the thing is that an engineer will understand that this particular part more and more forces and more stresses are generated. So this particular part, one can make some modification. What modification one can make? One can basically do a design modification, change the material, or one can do a selective laser heat treatment to increase the property here. So many engineering application, these things you have to know. So now come back and let's see what are the application from the basic application. You can see it's a tensile test. So everybody is aware about the tensile test. I expect everybody know what is tensile test.
Yes, sir.
Yes. Good. So everybody knows what is tensile test. So just let me ask you one question. Can somebody tell me that what you are going to get with this, which you are not going to get with normal tensile test? Tensile test will do, you'll get a stress strain graph or load displacement graph. So that load displacement graph or stress strain graph which you are going to get is going to get at one instant, maybe at the point where it has break. But if you know what is the properties at the top, or what is the property, okay, I thought somebody is wanted to add. So what is the property at different location, different points? That is something which you cannot tell. So in the finite element, you can see this is a von Mises stress. It is showing in the abacus. In the finite element, you can see from top to bottom throughout, you can get the property of the material. So this is what it actually happens. Similarly, this is a composite bar which is subjected to a high heat from the top, from this range, and you can see that you can study the conduction mode transfer. So how the temperature distributed in this particular composite metal. So you can see at the top layer the temperature is maximum, whereas the bottom layer the temperature has not reached. So this will allow the engineer to understand how and at what rate the heat conduction is happening across the system, across the component. Something which is not possible manually. In mathematical, you can only calculate. You can only calculate. But now let us just try to see how many points are there, that is the square mesh. So you can see 1 2 3 4 5 6 7 8 around in one line. You can see around there are 50 points. So there are 4 lines, and will be 200 points. So you can calculate the temperature, you can estimate the temperature at all 400 points. Otherwise, if in an actual sample, if you want to get a temperature at 400 points, you probably have to have 400 thermocouples installed, and that becomes a very, very tedious task, even to monitor, even to understand that each thermocouple, which location it is showing. So that becomes practically impossible. Something which is very practically impossible becomes feasible, not only for 400 elements but even for the 4000 elements. So you can clearly see, you can see this whole picture, something you cannot. So imagine you have heated a particular object. So that particular object, when you have heated, what happens when you heat the object? So you want to know where the temperature is very high and where the temperature is low and where the temperature is intermediate. So something you cannot see by looking at the object. But here in the finite element simulation, this picture you can clearly see, and you can tell that, okay, top layer the temperature is higher, and the bottom layer the temperature is very low, almost cooled. It's showing NT1. So what is the range of the temperature? You can see it's 25 uh, 2.5 into 10 to the power 1. So basically it has just started. So the heating has not yet taken place. So that's being put on the room temperature kind of. But once the heating will take place, what will happen, that this will keep on increasing. The temperature will keep on increasing, and location, you can see that which location has high temperature and which location. Now this is very interesting. Now, if something I'm telling you a completely industrial perspective now. So, and this is something which you will probably not see in the class. This is something which is very interesting. So you can see, what is this? This is a car. This is a car being crashed to a wall. So whenever a car design is finalized, one thing which happens in the car design is that
Sir, anything in video?
what?
You can see any video?
Video for this, for crashing?
Yes, sir. Yes.
Video I have not downloaded for the crashing, but there will be quite. You want to see the video from the YouTube will be there. So this is a basic presentation. So here what will happen is that this is all virtual testing. Okay, so in reality, if you want to know how much impact the car will have when it will collide, so you'll have to have so many cars and you have to collide that will cost a lot of impact, so a lot of cost for the company. So what you can basically do is that you can model a car. You can see this is a car which has been modeled in a finite simulation, FE simulation. Car has been mesh. You can see this a small mesh and everything. Then a front wall has been made here, and this wall is being made up of concrete material or whatever the material is there, and then this car at a certain speed being collided here. So you can see the damage over there. So from this they can study that how this whole damage thing is moving and everything and all. So this they can study from that. Again, similar thing you can see over here. You'll have the front on collision, you can have back collision, you can see what is the impact at the top, what is the impact at the bottom. Everything can be seen using the finite element. Otherwise, suppose if you have to do the same thing in a practical mode, so you'll have to have 4 cars, or each car you have to go from, you have to put the accident from the top, from the bottom, from the front, from the side, from the back, and you'll have huge loss of money. So something which you can make one model and then you can have those accidents, and then you can clearly see how much impact it is going to have on the passenger sitting inside. So what the engineers basically do, they want to have the toughness and resilience of the front structure as high as possible, so that even if it collides, the impact should not go to the person sitting inside at a certain level. Of course, beyond level, every material has a capacity, so it will go. But if you'll have a simple kind of thing, the impact should not reach. So this is the objective, which these are some of the practical industrial application which I'm telling you, which will not be taught elsewhere. Similarly, you can see this is the design of a mirror. So you can have different kind of design of the chassis structure and all. So this is the effect where you see the topology optimization. You can have different kind of design. Now this particular image here is very important. You see that when finite element software was not there in the picture, so you have this kind of design and this kind of traditional design, and when the finite element software has come, then you optimize the design. So you don't need the material here. What you have been able to achieve with this is a very lightweight component, something which all the car industries are now, automotive industries and aircraft industries are looking. So what does the lightweight component does? That it makes the weight of your car lighter. So maybe a car 20 years back weighs 500 kg. The same car now weighs 300 kg. So a 300 kg car will of course need less fuel. So your fuel economy and everything is saved. So this is what we can achieve using finite element. Something you can see, this is the original design of a model. This whole thing is 450 gram, and finally after doing the finite element optimization, the final design you get is this. So this is the final design which you get, and then you print it using the additive manufacturing process, and the final design came after the CAD reconstruction is 315 gram. So this almost 30% reduction in the weight. So if you can have the 30% reduction in the weight of aircraft, you can save millions and millions of dollars. In traveling, a company can get benefit with millions and millions of dollars. So that is the power of these kind of things, something which is not possible in a traditional setting. So again, you'll have the application of finite element analysis in the biomedical implant segment. So you have the CT image. CT image, why CT image? Because CT image is again an image of anything which is divided into many parts. So suppose you are making a tooth structure. So there you can have this image, and there, then you can have the material property, you can load those boundary condition, then you can perform the FEA model, and finally you can come up and see how much is the stresses which are acting there, and what is the load of the how much load can be applied so that the tooth, or the, if you are making the implant for the bone, that can. So even the finite element engineering application can be found in the biomedical implantation, biomedical field. That's why you see there are courses in the biomedical engineering. So now coming back to these are the different type of elements in the FEA package, which you can see over here. Then you'll have different element. We can see this. Okay, so different. What is the difference between the elements and the nodes? So you can see that these are the nodes, that the intersection points, and you'll have the elements which are there, which are inside the cross. This whole square. So one square comprises of 4 different nodes. So this is just the corner. So this things, now you can see again an application. This is an application, a tube welded application. Okay, a tube application which has been subjected to high deformation forces. So you can see that here this is weld. So this is a composite structure. Weld has been given a different property, something has been given a different property, and then this you can see that how the stresses are and strains are varying according to the locations. So opposite to the weld, here you can see the strains are very low, very less, of course, because weld is hard to deform, and towards the weld, towards the weld and opposite to the weld, you can see the strains are very high, something you can even plot, and you can see this 0 degree here, the weld is high, some all these things. So now these are different kind of elements. You can have a triangular element, you can have a square element, and the hexagonal element, and triangular element with 3 to 6 nodes. So we'll see this when we'll see the user interface. So all the elements have their own importance. So this is the some of the mathematics. I don't think that is important for you to understand. This is a part of course, I'll just skip that. Okay, and now coming back to this is the final part of our theoretical thing. So how to choose the mesh? So there are different kind of mesh. You can see this is a very fine mesh, and this is a coarse mesh. What is the meaning of fine mesh and coarse mesh? Means the mesh size is small. So suppose that you'll have to do the analysis of a component, very close nearby components. So this spanner, you can see you'll have from here to here, suppose the spanner is of 100 centimeter, maybe a 20 centimeter length, 20, 25, 30 centimeter length. So if you want to measure at every centimeter, every minute location, then you'll have to go over there and have to have a smaller mesh. And if you want to monitor at larger position, you can have larger mesh. But however, you can kill one thing which is very important to see here, which you will understand and very critical to see, is that in the whole thing you can see that this particular and here the results are completely varying. So this is a complete variation in result. Here you can see that highest strains are happening at this particular place, whereas here you can see compare the strains are high here also. So but in this smaller mesh the strains are not low here. So what does it really mean? That your choosing of the mesh becomes very critical. If you choose the wrong size of mesh, you will have a wrong result. So fine, this is like you'll whatever you'll give, it will come out. So now coming back to the mesh sensitivity analysis, this is why we do the mesh sensitivity analysis. So choosing the appropriate or good mesh size is very important part of finite element analysis. So how can you really know if the mesh is good enough for your analysis? So meshes are good enough measures, those measures which are good enough results with acceptable level of accuracy, assuming that all other inputs to the model are accurate. Of course, if the input to the model is not accurate, for example, in a particular application where the temperature is going up to 300 degrees centigrade, but in your model you have given the temperature only up to 100 degrees centigrade. So of course it will not be accurate because you have not simulated the actual conditions here accurately. But so this particular part, that assuming that all the other inputs to the model are accurate, is very important and very critical. Then only you will get a, so therefore the step 2 and step 3 becomes very critical when you are modeling and when you are giving the load condition or the boundary condition. So that becomes a very critical thing. Then you have the mesh density. Again, mesh density, you can see over here, this is a very fine mesh, has a very high mesh density, whereas this is a core mesh, has a low mesh density. So here you can see that mesh density and the element type and shape also affect the accuracy. So you can see clearly here. So you'll have a slightly different kind of results, different kind of mesh density, different kind of element size and shape and all. Okay, so greater the mesh density, better the accuracy of the result. So here if you'll see that this particular result is more accurate. However, the problem is that as you keep on increasing the mesh density, computational times keep on getting increased, and because of which you will face a lot of problem in the computational stuff. Okay, so what are the problems? There's highly dense mesh requires a large amount of computer memory and multiple iteration runs for conversion, and therefore it will have a very long runtime. So the trade-off, the challenge to in front of finite element engineer is that the trade-off level between the level of accuracy and mesh size is needed, hence the need for the mesh sensitivity. So you can see over here that how to choose the mesh. So you can see compare the test data with the experimental and theoretical data. So you can see that the mesh size, if the mesh size is very high, you'll have a very erroneous results, and if the mesh size is very low, you are getting a good results. However, you'll have to have those results in the range. So which is my experimental data? Something which is in this cross. So this cross, and here if you'll see this cross, you will see that this particular range, if you are going to get your data is accurate. So this particular range, the red and blue triangle are giving. So red and blue triangle means 1 and 1.5 mm of mesh size. So 1 and 1.5 mm of mesh size is giving our result, so that we understand that 1 and 1.5 mm mesh size is going to give us accurate result. So therefore we will choose 1.5 rather than 1. So why we'll choose 1.5? Because if we'll have higher mesh size means we will have better computational memories will be less, so computational time will be less. Similarly, here you can see the mesh refinement technique here. So this is a different mesh refinement. Again, you can see that this is a very fine mesh, and this is again a very coarse mesh. Some people are joining a bit late, so we are almost able to complete the session. Then you can see, okay, this is not very important. So you can see over there, this is a kind of mesh selection based on principle of result discontinuity. So you'll have different kind of mesh here. So this is called adaptive meshing. Here you can see the adaptive meshing which is being done manually. So some part of the mesh you'll have high meshes, coarse mesh, and some part you can have fine mesh. Those part which are much critical in analysis, there you can have the fine mesh size. Okay, so this is what adaptive meshing, that adaptive meshing adapt to the situation and consideration. Now here you'll have the global adaptive mesh refinement, again something which we can see. You can see that and you can understand this. You'll have the mesh size, coarser mesh size, coarser to finer mesh size we are going, and you can see that the finer mesh size giving a more accurate result. However, the drawback in this is that the user has no control over the mesh. So once the calculation starts, the mesh distortion will take place, and the user can have excessive mesh refinement may occur in one region, which is the region of less interest, whereas the region where there is a larger local error, that that is where the high error that becomes unacceptable. So therefore the local adaptive mesh refinement is done, and in it is possible to refine the mesh in this locally, so where you can identify which particular area is your critical area. So if you can see now here all the mesh are almost uniform. Coming back to here, you identify that this particular area, and this particular area is my more critical area. However, there's not much happening in this particular area. So here you can have the mesh which you can choose that we do not need to refine the mesh. However, here you can see that we can do the mesh refinement because this is our critical area, and that is how you can do the mesh refinement. And finally you can do the manual mesh refinement. Manually you can choose. So this is the automatic mesh refinement, okay, local adaptive. But manually you can choose. So manually you can select each area one by one in your model, and you can see that this particular more area which is not critical for you, so you'll have a very coarse mesh, and this area you have chosen. So this particular area have finer mesh, this area has less finer mesh, and this area even more finer. So you can choose the area one by one and you can define that. So this is about the basic of finite element, from basic to some advanced level. So now if you can have any doubt, you can ask about the doubt, and then we'll see the user interface of the Abacus CAE, Abacus software. Yes guys, anybody want to ask any question? Somebody wants to see the video. Let me just, I have the video in my laptop for this, but here I do not have the video. So you ask the question. Anybody who has any doubt? Any connection? Just.
Sir, could you send that PPT in WhatsApp?
I'll see whether we can send that or not. I'll talk and I'll tell
Okay,
you.
sir. Okay, right.
So somebody wanted to see. So these are some large videos. So I just wanted to show you the last video you have to see. This video will probably have what you want to see. Okay, but there's slow net connection. So you can see over here that what they are making is a model, mesh model. So this two car models has been made, and finally they will give the displacement. So what they will do is that for this particular car, so in an industry they are doing the car crash analysis, so they will see the displacement. So this car will be given displacement in this direction, and this car will be given a displacement in this direction. So we'll have two cars, one car, this one, and the other car. So this simulation will have two parts. You can see over there, if I can increase this, you can see two parts, car 1 and car 2, and this is the name of the program, this is the name of the job, car crash, so don't need to worry. So car 1, if you'll have, what they will give is that they will give it the displacement in this direction. This is your part of your job boundary condition, and the car 2 they will give displacement in this direction, in this direction, if that is okay. So now they have meshed. This is the final mesh you can see, and this is how you see. Now just see the video. So this is how they collided. Okay, this is how it has collided. So you can see that how the changes are happening. So here you can see that the maximum impact will have in the front. However, in the back, you can see, and it's a common sense. So everybody know that the impact which we are going to have at the back is very less, whereas the impact which we are going to have in the front is very high. So that is a common sense. That's something which everybody knows. But how much impact we are going to have? So you can see how much impact is going to reach. So passenger will be sitting somewhere over here. So this becomes a critical area. So what is the color of this? The color of this will be green, and the color of this will be yellow. So if they will look at this, and they'll see how much the stresses which are being transferred. So they will see that this is small, so they will see the stresses over there. What is the stress of the yellow color or and the green color? And based on that, if they will realize that whether this particular stresses are actually uh, bearable for the passenger or not. If it is bearable for the passenger, it's fine. Otherwise, if it is not bearable for the passenger, so what they devise is a airbag. So the moment there is a kind of a crash, the airbag suddenly opens up, and the passenger is filled with airbag, and that uh, he can get safe from the accident. So you can see this. This is a much better picture. So not from the side on. Let me just see. So this area, you can clearly see this area completely got damaged because it's showing red, and red will have very high stresses over there. So it will of course not run this area completely. But the critical part for the engineers are to analyze is this particular area, right? This particular area is a critical part because that is where the passengers are sitting. So this is just one type of collision. This is a head-on collision of a car. Similarly, you can have a back collision and everything. I can see if there's a video available for that or not. Another car crash structures is there. So let me just, I have these videos, but this is not my laptop. I have a problem with my laptops. Okay. So now you can see this again, very interesting. So what is happening here? Just let's go a bit back. Yeah. So now what they are simulating over here, try to understand. This is again very important. This is kind of a tower. So suppose your car is moving in a road, and then sometimes it collides with the tower, or it collides with the wall, it collides with the building or rod or something like this. So this is a tower. Now if you want this to be rod, okay, so you give a property of steel to it, और रॉड whatever the material the rod is होता है जो, और column जो होते हैं. So if you want to simulate the whole thing, the whole crash incident with the rod, so you can give the property of steel to it, and once you'll have the property of steel, you will collide it with. So what you will see here, that how the car will impact if it will collide with a steel rod which is there in the, and suppose if you want it to collide to the wall, so wall is not made up of steel, it is made up of stones and concrete. So you don't have to rerun the simulation. What you can do is that for this particular thing, you can give the property of concrete to it, property of stone, property of concrete to it. So you can have one simulation, you can only change the property, and then on the basis of that you will get the result that how the car will get impacted if it gets collide with the wall, or how the car will get impacted. So here you can see in the simulation, you can see here, this is just a model, this is not the finite how it is impacting. Okay, let's slow. So now this has, the car has collided. So you can see these values are increasing. If you see the values here on the right side of the S minus strain, so this value, or they have fixed the value constant, but the color coding is increasing. So just go a bit back. Now here you can see here everything is blue. That is, it is normal. The stresses acting are very small. That's not very high stresses. However, as it is getting collided, you can see this color is changing. Okay, now it is freeze, it collided, it just has touched the wall. So now this is slightly yellow from 25, whatever the unit they have chosen, maybe megapascal or something, when 25 megapascal is very high. So from 25 megapascal, it has gone to this color, and the color is how much? Yellow. 225, 2.25 to the into 10 to the power 2. That is 225 megapascal, almost 10 times more stresses. Let's move further. Let's see. Now it is getting distorted, and the impact is coming even at the back. Okay, so now you see what has happened. The whole structure got crushed. Whole structure got crushed, and the impact has come up to this place and somewhat here. So the passenger who will be sitting over there, he will be safe. So with this kind of car crash, this design will be passed. Okay, because the passenger will be safe, because the thing over here where the passenger will be sitting in this particular location, the stresses are not varying. Let's see some other. So you are here, what you are basically doing is they are changing different parameters. So this is a deformation parameter, how much the body of the car is getting deformed. So now you see just 1 second. Let me, yeah. So here you see the magnitude, how the magnitude is changing. So this is almost cream color, so no deformation yet. And then you can see the color is changing, right? So now the deformation in this part is more. So what they are changing here, you can see over there. Let me just go back to it. Yeah. So here they are this primary results. So you can see this is the plastic strain, this is the equivalent strain, this is the uniform deformation and everything, displacement, sorry, how much is impact is having on the body when it will distort.
Sir, any command is software.
Yeah, we'll see the, now we'll see
You
in
explain
the,
yes, sir.
yeah, what?
You explain the afternoon session, sir.
Yeah, we'll explain the afternoon session, we'll see, explain the software. The
Okay,
software,
sir.
the interface and the command, and we'll see the application there, the time permit.
Okay.
So because this session is combined with the tomorrow's session. Okay, so the today and tomorrow session will have the combined FEM analysis. So the whole session is combined. So today and tomorrow session will have theory plus the software. So those who have joined today, they need to join tomorrow as well. So therefore, the first session will be theory, and the next 3 sessions will be on the hands-on software analysis.
Okay.
Okay, so now anybody, there's 5 minutes left. So anybody have any doubt about the presentation or other thing, the application, any other application, anything regarding the subjects and everything, you can ask. So anybody wants to ask any question?
Oh, sir.
Car crash or whatever we are going to analyze, how can we get the exact value or data of any point? Okay, this is a good question. So this, you have to understand that there are 3 things. Exact value of data you are not going to get with your experience. So suppose you are driving a car in a city, so at what speed the car will be driven? Maximum you can say 30 or 40 or 50 kilometer per hour, right? So 50 kilometer per hour, if the speed is there, so you will give the speed of the 2 cars at 50. That will be maximum, because the maximum impact you are going to have with the maximum speed. So if you are checking for the car crash in the city, you'll say you'll give a 50 kilometers. Similarly, if you're checking for a car crash in a highway, the highway may be 80 to 90 kilometer, but highway generally there's very little possibility of head-on crash. So you'll see where is the maximum values over there, and that particular maximum value you will put in terms of crash analysis, and there you will get the whole formula. So that you will give in the boundary condition. So there are 3 steps. The first step is to make the car design model have the same material as the material which you are going to use in the industry for the car. So for example, in the front you are going to have aluminum, if the back you are going to have steel, then you'll have going to have titanium. So have model the car of the same dimension and same shape, then give them the same material properties which you are going to manufacture the car with. Okay, and then give the speed to them the same. So suppose you are modeling for maybe 100 kilo, what will happen to the maximum impact may happen 100 kilometer per hour. So suppose 2 cars are coming at 100 kilometer per hour. So what is the impact it is going to have? So the industry people do get those data, ki jo crash, whatever the crash is happening, that crash is happening at what speed and at what collision speed and all these things. So therefore the design, the safety standard is different for different places. Okay, I'll come to it. So the safety will be different, will be generated, and the safety data is different for different cities and different places. So that you will give. So step 1 is to model the car, exact shape and dimension. Step 2, give the exact material properties to different parts of the car which you are going to monitor. Step 3, decide the speed at which you are going to have the collision, and give the same speed or different speed maybe to different cars, and then you can have the collision and you can basically see what you are going to get with that. So this is the exact value of the data point. And the second question will be, will there be report generated from the analysis? Yes, of course. There is a whole setup where you can get the whole report generated, that with respect to the time, with respect to the overall things, how we are getting a different kind of different kind of performance and whatever is the outcome which you want to. So you'll get the report from the analysis in form of the Excel sheet, and then you can plot it. So let me just show one example there of simple tensile test. So, so you'll see over there that the report is generated. Okay. So yeah, here. So you can see the whole stress strain diagram and everything is getting generated. Everything you can get there. There are procedures, there are steps to it, and it's a very vast software. Okay, the whole objective is to just give you a basic insight of finite element and basic user interface of these softwares. So you can see these are all models over there. You can see all, and those results are generated in your Excel sheet, and then you can plot it basically based on whatever results you basically want. So all the results you can get generated using the software. Any other question?
Yes, sir.
Yes, ask. Please ask.
सर ऑटोकैड और सर कैटिया सीख लेने से सर वो मैकेनिकल डिज़ाइन इंजीनियर सर वो कहलाएगा?
नहीं देखो engineer you will only be called. Okay, there are some international students, so let me just tell you what he has asked. So he has basically asked that if we'll learn AutoCAD or CATIA, will we be called a mechanical design engineer? So no, you will not be called a mechanical design engineer learning simply AutoCAD or CATIA. You'll have to have the engineering degree for that. But AutoCAD and CATIA software will give you a basic insight of solid modeling, okay, which is something which is very necessary and very important for the finite element, because how you will, if you don't know the solid modeling, how you will make the uh, you'll make the model in your software. So of course abacus will have their inbuilt model and everything. So you'll have to have this particular thing over there which you have to understand. Otherwise, for those AutoCAD and CATIA, that's why see AutoCAD, CATIA Pro session have begin, and then we are coming back to FE analysis, finite elements. So those are prerequisites. Okay, but merely by learning AutoCAD and CATIA, you may get a small job of maybe some solid modeling and designer kind of, but you will not be a pure engineer until you'll study all these things. How can I use?
Okay, sir.
How can I use? Okay, next question is how can I use different platform model for analyzing? Suppose I want to make a model on CATIA, so how can I use this model on Abacus? So you can make a model over there and then you can import the Abacus. So I'll show you there. Let me just go to the interface. Our time is already getting over, but because you have asked the question, so let me just carry. So you'll have, suppose you already have a model somewhere in the file, so you'll have this, okay, file, and then sorry, you'll have part, you'll have an option over there, import, and then wherever you have the model, you can choose the model from your software and then you can import it, and you don't need to make the model. So if you make the model uh, from the different software, you can directly import, but the only thing you have to keep in mind is while importing the software, while importing the model, the file in which you have saved should have the same extension as the one which Abacus or whichever software you are doing is supporting. For example, I worked on PAMStamp, so PAMStamp have IGS files format. So if you made a particular model in different file format, then it will not support. Okay. Yes, Momin Abdullah, what is your question?
Sir, for installing this software, is student can get software from any source?
For this, to get software from source, so I don't know. Yes, there are certain sources available, but to be honest, that is not very legal. Okay, so if you are,
Okay,
that's
sir.
why if you have the antivirus installed in your softwares, so what will basically happen is that antivirus may detect those softwares. So generally, when we were there at IIT, we are not permitted to use the crack version, but yes, the crack versions are available outside on some of the website. I don't know. I don't really know those website, but there are this. You can contact the resource persons if you know anybody, so that they can arrange softwares for you. But that
And
is
sir, one more
technically
question.
speaking, that is illegal. Yeah.
सर वन मोर क्वेश्चन सर, जैसे कि एक ऑफलाइन क्लासेस होती है और ऑनलाइन क्लासेस, जो कुछ क्लासेस तो फ्री में प्रोवाइड करती है सॉफ्टवेयर, पूरा कोर्स जो होता है, जैसे कटिया का है, सॉलिड मॉडलिंग का है, तो सर उसके ताल्लुक से आपका क्या रिव्यू है?
Yes, yes, you can do those courses online. Wherever you learn, you'll get the opportunity to learn these softwares because you'll be graduating next year. So I think it is very, very important for you guys to be at least aware of these technology. That is the objective. That is one of the objective of this course, to make people aware of these technologies, because in many of the engineering college, people are not even aware of. So I could have straight away gone to the software. Many people would have wanted, but if I would have gone to the software, you would not be understanding those basics. So if you don't know the basic, then it's just like there's no point in doing all these things.
सर कुछ स्टूडेंट्स क्या कहते हैं कि
If
जैसे
you get the
ऑफलाइन में।
learning opportunity,
यस
okay,
सर।
for these softwares online, you definitely adapt it. And if you're not getting learning opportunities, at least you can watch these videos, so that you should be aware of this interface. Abacus especially, there's so many videos over there. So you should be aware of the interface, and you can know what it is. So the moment somebody will ask you, can you work on Abacus, you'll say, yes, I can. I know the interface, I know the things, I know that. So just a bit, 1 week of training and I can work on Abacus. But if you don't even know anything of softwares, any idea, ask you to teach, somebody will teach, you will not understand that.
ओके सर, थैंक यू।
Okay, thank you. So now we'll wind up this session, and next session we'll see the user interface of Abacus and some of the basic problems. So thank you very much for attending. Thank you very much. So now I'll leave.
Actor sir.
Yes, what happened? Who is there?
Okay. Mic. Okay. Okay, everyone. Thank you very much for attending this session. And I ask you to join the next session that will start at 2:30 p.m. We will be covering, we will be going through the Abacus hands-on session, and there will be some problem as it was done in earlier sessions. So be there on time. We will start sharp at 2:30. Thank you, everyone. All of you are now free to leave.
यस सर, थैंक यू।
Sir, thank you.